So there, now we'll discuss about zigzag transformers. So these kind of transformers, basically they are used in power electronics converter circuits where we want to eliminate the harmonics. So, but I'm not going in detail with there, but I'm just want to introduce this kind of transformer connections as well, which are possible, and there are various possibilities of it, like star zigzag star and delta zigzag star. Okay, and obviously various groups as well, like minus 30 degree, plus 30 degree. These are all combinations possible here. But I would be just discussing in brief about the star zigzag star connections here. So in this type of connections, basically there are the primary is as the other normal convention star transformers, like we have seen before. Let's say A1, A2 here, B1, B2 here, and C1, C2 here, and these are the dots here. And if you make the neutral point out here, so that makes the star at the primary. But the secondary, I would say in the secondary side, each phase winding is equally splitted. So if this number of turns, let's say it was 1 here, so this is N2 by 2 and this is N2 by 2. So overall in one phase, if you'll see, the turn ratio would be like N1 upon N2. If you'll see, that turn ratio is actually A. And as per our requirement, basically we can make various combinations out of it. So basically if you'll see, let's say this is I would say A4 here and A3 here and A1 here and A2 here, and the dots are marked on the odd numbers, right? Let's say, because if I see a single limb here, one limb for one phase, so if you have a primary winding here, okay, and this is N1, so in the secondary you have N2 by 2, and then you have another winding as well. So let's say this is A1, A2 here, and on this you would be having A1, A2, and then again this is A3 and A4. So obviously the dots are here, and the dots for A1, smaller A1 is here, and for this the dot would be here. And you see here, like, so these windings, this is for one phase I have shown. Similarly, what I'm trying to say is this is N2 by 2. Okay, so the secondary winding is split into 2, and similarly for the other phase as well. And similarly C2 here. Okay, so if you see the phasor for it, for each phase, let's say the phase voltages here, if they are at this angle, and these are all connected at neutral, so A1 here, B1 here, and C1 here, and this is the neutral point, and this is the neutral point here for all these three. Okay, similarly for the other one, these would be the phasors. Let's say if I have already connected here with the source, obviously then only this voltage phasors will appear, right? And these are A, B, and C, AS, BS, and CS. Okay, so we have here, I would say A2, A1, A4, and A3, right? Similarly for C phase, C1 and C3 here, the even numbers here, and B1 and B3 here. So in zigzag transformer, what we do is basically we choose one phase of this same, like one winding of the same phase and other winding from the other two phases, and we will see that the combinations which are possible there. If you'll see that, let's try to make those combinations. So I'm just choosing the reverse of phase A winding first, and let's say I have choose this winding, because generally I used to tap load at the A1, B1 and C1, the smaller A1, B1 and C1. So I will keep that winding for the load connection. So I will say, okay, A4 I have done the connection here. Okay, means in the reverse direction, and I am forming the neutral with these only. So if you compare with these phases, the above phases, this would be their actual original phasors, right? But I have connected in the opposite way. That means instead of forming A4 as the neutral points, A4, B4 and C4 as the neutral point, what I have done is I have formed A3, B3 and C3 as the neutral point here. So I have actually shorted these as the neutral point. So this is the same neutral here, let's say N here. So this is the neutral point here, N. Okay, so if this is A4, this would be C4 and this would be B4. And I am using this winding, this the winding A2, A1 for the other combinations. Let's see. So if I am using winding A1 here, okay, so this is A1 here, and similarly for this, so let's see if you see the combination, I have used C4, I have connected C4 with A2 actually, right, and C3 is here. Similarly for A4, so and if you see the resultant here, resultant of these two phasor quantities, that would be this, and obviously this angle would be 30 degree, because this angle is 30 and this angle is 60, so this angle would be 120, and then this angle would be 30, so this angle is also 30. Okay, then you see I want another phase voltage, okay, which is at 120 degree to this, right, and this is only possible if I choose the phase B here, right, phase B, these combinations. So I would be choosing B1 here, which is in parallel with this, and if you see the resultant, that resultant would be this phase. So this is B1 here. So this will go to load A terminal, load B terminal, and I want the resultant at 120 degree of it. Okay, so then I would be choosing phase C here, which would be parallel to this. So phase C here, and so this would be actually phase C here. So if you see all these three phases, they are at 120 degree to each other. If this was 30 here, even this is 30 here, right? So this makes 120 degree between these two, and this is 120 degree here, right? So this is my terminal, I would say C here. Okay, that's how. So I have actually connected a phasor with a terminal. But what I'm trying to say is actually this point would be my terminal A, this point would be my terminal B, and this point would be my terminal C. And here I have connected C1 here. Okay. So if you compare this phase voltage, the red one, with this phase voltage, okay, so they are at 30 degree to each other, right? So if I plot the line voltages here, the line voltage is AB, okay, even that would be at 30 degree to the line voltage of the primary side as well. Okay, so this combination is basically, I would say, star, zigzag star with minus 30 degree. Okay, and if you see the transformation ratio, if you find for the, let's say for the phase one, if you have calculated, let's say for the primary voltage transformation ratio is A:1, then for line voltage transformation ratio, or sorry, not primary voltage, rather phase voltage transformation ratio, if I'll say, phase voltage transformation ratio is A:1, then for line voltage transformation ratio would be 2/√3 A:1. Okay, you can easily compute that one. Let's say, because this is, if you see this section only, this is smaller, this section, if you see this section, actually just this section, okay, this is obviously phase voltage I have taken, and this is N2 by 2, right? N2 by 2, half of it. So I'm just taking half here, and even this is at half. And if you see the resultant of it, okay, so that would be 2 times of 1 by 2 of cos of this angle is 30 degree here, cos 30 degree, and if you calculate, this will come out to be cos 30 degree, which is root 3 by 2. Obviously, this is for the phase voltages. This is this magnitude, the red one which I have drawn here, they are the phase voltages. Then you need to compute the line voltage. Obviously, in a star connected line, in a star connected circuit, line to line voltage is root 3 times the phase voltage. So that would be root 3 by 2 of the phase voltage here, that is 3 by 2. Okay, and if you calculate the turns, if you find the ratio, transformation ratio there, these ratios, you will actually get this ratio there for the line voltage transformation ratio. This I have drawn for zigzag star connection for minus 30 degree combination. The same combination for plus 30 degree is also possible, and for delta as well is possible, which I am not going to take here. But even that can be drawn easily. With simple logic, you can easily draw those combinations as well. Okay. So for all these kind of connections, 3 different connections in 3-phase transformer, we have talked about star-star combination, star-star connection, star-delta connection, and delta-star connections, delta-delta connections. And then in delta-delta connections, we have seen about the open phase, like V connection, right? Open delta connection. And then we have talked about Scott connection, then zigzag connection. So these are different combinations possible. Okay. Basically, we should know the where to use which kind of connections. So basically, I have said, right, the star delta connection is mostly used, and delta star combination. These 2 type of connections, they are basically used in the transmission line network. Okay, and even delta star combination is used in this at distribution level as well. Okay, because let's say in distribution level we want a single phase supply as well. So we have actually in that case, the star will be connected toward the low voltage side. Okay, let's say the star delta combination in the transmission level, at the transmission level, basically the star side is connected at the high voltage side, and delta connection is done at the low voltage side, because of there inherently at a star side is having higher turn ratio in terms of line voltage, if I talk about, and in delta connection we have the lower turn ratio. That's why we keep this star combination at the higher voltage side. But in distribution level, where we generally, as a common user, we get a single phase supply, there we will use a delta star combination. In that case, the star combination would be given for the low voltage side, and this will actually cater, it will solve 2 problems. One is the unbalancing problem as well, and the second thing is neutral is also accessible to the loads, right? So if we want a single phase load, if you want to connect a single phase load, so we can tap one phase and one neutral of it easily, right? So in distribution level, we use delta star combination, where star combination is at low voltage side. Okay, and this unbalancing, if you'll see, that won't go beyond the delta connection, because all those unbalanced current will circulate in the delta combination only. Okay, you think of the phase current in the secondary is unbalanced. Okay, so that unbalanced current, that will reflect in the primary side as well. And now since this is delta connected one, so all these, the sum of these current will actually won't be 0, and that will flow within the delta network. And the line current will have, you know, a balance. The sum of it would be IA plus IB plus IC would be 0 there. The line current would be balanced there. Okay, so that is the use there. And this zigzag transformer, we said that we use it in power electronics circuit, basically in rectifier circuits. There we use it for suppressing the harmonics as well. So which I am not taking here. Okay, now we will talk some problems associated with some general discussion, and some problem associated with 3-phase transformer.